Okay, so the first thing, this is Sociology 101. You guys are in the wrong place. You should leave the Zoom. I'm just kidding. It's Organic 2, chem335. And this is the public website. It's also on the syllabus. It's all linked to the iLearn. So everything that's kind of like related to the course, including PowerPoints and stuff, is on this public website. You don't need to use iLearn to get here. You can make a link to it. And we already see some of the stuff we'll be talking about. Chapter 10 will be where we continue from Organic 1. It's the NMR chapter. This is also where I provide some kind of optional homework assignments and reading assignments. I really think you should do those things, but they're not required in the course. So you can see for chapter 10, like what parts, what sections I recommend reading, and also there's some assigned homework problems. But those are again optional, and it's going to really your success in the course will depend on how well you understand stuff, and doing the homework problems is a good way to test yourself. Also, chapter 10 has a series of PowerPoints. They're not, it says there's 7 of them, but they're not all full, course periods. I would just download them all. There's like 2 styles, depending on how you like your PowerPoints. I think style 2 might be what you guys like the most. And let's see what else. You'll see what NMR is in a second, but there's a really cool online utility that you can play around with as you get more comfortable with it. You can basically draw a chemical structure and then get the NMR spectrum, which is it is actually kind of educational. First, you got to learn what NMR is, and then you can play around with this tool. And then after we're done with chapter 10, we'll get into chapter 13, which is kind of back to the normal organic chemistry you're familiar with, alkynes, which is kind of like alkenes, right? But it's a triple bond. Okay, and then as we go along, I'll add the additional chapters to this. Okay, so where's the syllabus? The syllabus is on the top left here, and let's go through the syllabus. Okay. Okay, so as you guys know, the course is going to be Zoom for a couple weeks, and then we're going to go back to in-person. If you are actually assuming the whole course is remote, you won't be able to complete this course because all the exams and everything are going to be in person. Anyway, so yeah, we're Tuesday, Thursday, 5 to 6:15. These are the office hours, which I actually kind of designed to be not conflicting with people's other courses, which it took a while to find office hours that are, there's maybe a little bit of conflict, but for the most part, these office hours don't conflict with people. This is that public website I was just showing, which is also linked on the iLearn. You need Organic 1, of course. You guys all have Organic 1 by now. The required textbook is Volhard and Shore 7th edition, which I think you should all have, from Organic 1. There's places you can download it. You can also find it on, printed copies on Amazon, pretty cheap, $20 maybe. It's a great book. It's really good, and we often use the older editions to make it a little cheaper for you guys, right? Organic chemistry as a second language is also kind of like a nice source of like problems to challenge yourself. I'll show you the schedule in a little bit and how we do the exams. But if you took my Organic 1, it's the same exact way. But basically, there's 4 midterms that are 100 points each, and we have a cumulative final that's 100 points also. Kind of like 5 exams. The last midterm and the final are on the same day. It's like a double final, basically. And we drop the lowest of exams 1 through 4, but we don't drop exam 5. Okay. Anyway, that's all far away, and you can read this and understand it. But it's it's a pretty reasonable grading system that we've used. Okay, and we don't I don't want to say we never curve the exams. I mean, if there's an exam where everybody kind of does a little poorly, I might give everybody a couple points. And so that's kind of a boost of the average, but that actually doesn't happen super often. So we'll just see how the exams go. Okay. Also, we have a great exam grading dispute policy, which if you do this, you just need to do it by the next exam, so you can read about this. The homework problems are suggested, but they're not formally assigned. Office hours are a great time to kind of go over homework problems and also exam problems, and sample exam problems as we get there. But if you're trying to just keep on top of the material, doing the assigned homework will really help you. Also, like I said, we have the course website, which is my external website. Just make a link to that on your phone or computer or whatever. We use iLearn, but not as much as other people do in courses. The main use of iLearn is going to be for like discussion forums, which I think is underutilized. You guys should really ask questions on iLearn. I think it's, it also lets people sort of help each other out, students. I also think, especially as when we're face to face, study groups are a super useful thing. Just to meet people and actually kind of struggle, we'll say, struggle together, and you can kind of teach each other, right? It's a really useful thing. So study groups, trying to meet a couple people that have a similar schedule, and you guys can maybe go meet in the library. It really does help, like on the exams and things like that. Okay, be punctual to iLearn as well as to the normal class. iLearn I will be recording, so I still think it's a good idea to be punctual. Exams must be taken in pencil, not pen. That sounds totally silly and trivial. My main thing though is with a pencil you can erase it, your answers, and with a pen people just scribble everything out, and it's just a big mess. So it actually helps you guys to use a pencil with a good eraser. Get one of these crazy big erasers, and a nice mechanical pencil. That's the two things you really need in this course for exams. And I also think notes. I was also going to say you should be taking notes through the course, especially once we get into the reactions, the alkynes and things like that, because that's where you're going to be studying from. And so taking really good notes. This is one of these courses where you just, a lot of it is I'll be teaching and you'll be copying stuff down. Some stuff's PowerPoint and you're not going to be doing that, right? I mean, if a PowerPoint course, you might take little notes, but you're not writing everything I'm doing. Well, you should integrate the PowerPoint notes into your notes, and then you can review that, right? Anything I teach you from PowerPoint is fair game for the exams, so you do have to study it and look at it again, all right? Students seeking a letter of recommendation needs a score of 80 on all 5 exams. Now I have some wiggle room there, but the big thing is I don't want people to, if you're going for a letter, to skip exam 4. Remember, there's that 4th exam. If you're doing really well in the course, you could skip exam 4 and get an A in the course. But I'm trying to have, if you want a letter of recommendation, I don't want you to do that. Let's see. Cell phone ringers, you guys know about this. This isn't really a PowerPoint course. A little bit of it's in PowerPoint, though. The majority of this is really going to be on the whiteboard. And I'm also, like, when we teach remote, I'll kind of have it like a webcam and I'll draw chemical reactions and mechanisms and stuff. So it's going to be kind of like a virtual whiteboard, okay? But most of the course is really reactions and mechanisms and synthesis, and it's all going to be on the whiteboard. You all got to copy it down and study it. Not really extra credit. Here and there, I'll give you a couple, a point extra credit problem on the exams. Earplugs is a really cool idea for exams. If you're distracted at all, bring earplugs along with your pencil and eraser. as far as I know, the department's not allowing credit, no credit grading anymore. Somehow people did it last semester, although it's not formally allowed, and I don't know. I was told we can't really allow it anymore. So it's on the syllabus. Here's the grading scale. Okay, other strategies. I already kind of talked about this. Be punctual. Read the textbook. Do the assigned problems. Try reading ahead if you can, if you have a little bit extra time. Reading ahead is always a good thing before the lectures. And also combining your lecture notes with the textbook readings and oh yeah, recopying your notes. Sounds crazy. Why would you spend time recopying your notes? If you say you copy 10 pages of notes, why would you want to recopy them? Because if you do that after a class, maybe you know, in the evening, you actually will learn the material better because you're copying it and looking at it again, and then it gets absorbed into your brain. Any hard class you guys take, recopying your notes is an amazing thing. Somebody said, I thought it was ever, yeah, somebody said about credit, no credit. I thought it wasn't ever allowed, and it was kind of a quarantine thing. Yeah, I asked the chair of the department, and he said that the college doesn't really allow it for chemistry and maybe other science courses. I don't really understand the policies. I don't totally understand that. Yeah. Okay. If you do this recopying of your notes, your notes will look nicer, and when you have to study for GREs and MCATs and things, it'll be better and you know, easier to study and look back at your notes. Having kind of horrible scribbled down notes aren't that useful, but recopied notes are really good. Okay, also index cards. Index cards, when we start getting into a lot of reactions, and that's going to be, you know, after chapter 10, it's all reactions, like a million reactions. Index cards are a great way to study that. Like, I can give you some ideas for that, but like have a reaction examples, you know, on one side of the index card, and then the mechanism, because I test you over the mechanisms. On the back side of the card, you can kind of study it a little more effectively and practice, kind of like a foreign language, right? I actually, when I made the syllabus, I was kind of suggesting like a, well, maybe outlines. I do think index cards are a good way to do this. I think more recently, students have had a lot of good luck with index cards. When I took organic chemistry, I would like make an outline. Like I'd learn a chapter and make like a 2-page outline of the chapter, and that was kind of useful. But now I think index cards are maybe the better way. There are some apps, and also Khan Academy is a good thing to supplement your lecture materials. Oh yeah, it's not on the syllabus. You might write this down. I taught the entire course remotely in, when was it? Spring of 2021, I guess last year. And all of my lectures for the entire course are on my YouTube channel, and it's MXA SFSU. So if you would maybe miss a lecture during the normal, you know, in-person class, which you should never do, that can actually really hurt you if you miss class. But if you absolutely have to miss class, you can go look at those videos from a year ago. All right, I have the entire course recorded from last year. That doesn't mean you shouldn't come to class. Doesn't mean you shouldn't come to Zoom, because you're going to really, if you get behind, you're never going to catch up. So, but if you do need, or if you need to like review a topic like some kind of alkyne reaction, you can go look at the alkyne videos, right? Okay, so that's YouTube channel is MXA SFSU. All right, what else do we got here? Here's the schedule. And as you see, first couple weeks are Zoom, and we're mainly going to talk about chapter 10 and chapter 13, the alkyne chapter. We're going to get into chapter 15 and also 16. Now, normally the first exam would be on this day here. Would that be February 14th, 15th, February 17th. Normally, we would have this first exam on this date, and that's going to be in the in-person period, right? But since you'll just be getting into in-person learning again, I don't want to have the exam immediately then. So you can see that I pushed the exam 1 onto the next week, all right? Exam 1 is only chapter 10 and 13. So you will have to like really learn those 2 chapters, chapter 10 and 13, learn them as good as possible. And I even give you the exam 1 sample exam and stuff, you know, back a couple weeks before. But because of the way the schedule is set up, I decided to put exam 1 a little bit later, okay? Now, the one annoying thing is that exam 2 is going to be pretty quick after that, but then exam 3 is way down the road. It's just the only way I could do this scheduling and be able to do the exams in person, all right? Okay. Okay, so anyway, otherwise this is, you know, chapter 10 is NMR. And then we have chapter 13 alkynes, and the rest of these are just chapters with different reactions and functional groups and things. Aromatic, you know, the benzenes. Chapter 16 is more aromatic synthesis. Chapter 17 is carbonyls, C-double-bond-O. Chapter 18 is called enols and aldols. You don't know that yet, etc. And chapter 19 are carboxylic acids. Chapter 20 is carboxylic acid derivatives. Remember things like esters and amides. Remember those functional groups? Amines will be 21, and then you're almost done with the course at that point. 22 is more aromatic stuff, a little more aromatic. Chapter 23 will be a little more ester stuff. But that's the entire course right there, all right? Generally speaking, I'll have some exam information and sample exam stuff posted the Friday before the exams, okay? And I may have some kind of review session at the very end, but that's far away. All right, anything else? DPRC students, if you are a DPRC student, you get extra time in the course. Contact me and contact the DPRC office. There's a policy against sexual violence that you can read about on the syllabus. Teaching methods, mostly it's, you know, whiteboard, PowerPoint, and, you know, and I do the best I can using remote learning to accomplish that also. We also have a set of student learning outcomes that are on my website here too. Okay, is that it? NMR correlation charts. So these are going to be your friend very soon as we learn NMR. These will also be available on the exams, but we first got to teach you the basics of NMR. I don't know why the carbon one didn't show up. I think it's in the PDF. Okay, all right. So anyway, you guys can download the syllabus from my website, right? Okay, so let's get into first thing I want to talk about is the one second. Concepts you need from Organic 1. So Organic 1, if you might remember, was kind of hard. It was not an easy course. Yeah, it's lower division. Organic 2 is upper division. They both should be upper division. They're really hard courses. And there's certain things you need to know from Organic 1. And if you don't, you can quickly try to relearn them. But if you do not have some key concepts down from Organic 1, you're going to have a lot of trouble in Organic 2. So that's why I mentioned a couple of these key topics. All right. Oh yeah, this is the official textbook, Wohlhart Shore 7th edition. 6th edition is probably okay. A couple of the homework problems aren't synchronized, but for the most part, you can get away with the 6th edition. McMurray, we haven't used in years, so you're probably not using. Probably none of you are used McMurray in your Organic 1 course. But the big problem with other textbooks, especially if you're a transfer student, is if there's certain chapters you never got because there's a different arrangement, it's going to hurt you. And like chapter 8, 9, and 11, and 12 from Wohlhart and Shore are really important. And If you never got them, you need to learn these chapters very quickly. Okay. Okay, so I'm going to show a couple old reactions from Organic 1. This will just get us all kind of primed for Organic 2. We're going to mention the reagents, the regiochemistry, which kind of means Markovnikov and anti-Markovnikov. You're not going to see mechanism questions from old reactions, but you kind of just need to know the basic reactions because this is a cumulative course, right? And this is why, that's why I'm showing this PowerPoint. Most important reactions for synthesis questions will have asterisks as I go through this. All right, so these are just a couple, miscellaneous reactions from the old days of Organic 1. Oxidation, so PCC will oxidize a primary alcohol. This is a primary alcohol because there's only one thing on the alcohol. It oxidizes from an alcohol to an aldehyde. To go further, you can use CrO3 in acid water, and that makes a carboxylic acid functional group. Or you can just skip all that and just go straight in one step from the alcohol to the acid. And then reduction, you've never learned a way to go from the acid to the aldehyde, and there actually is not a way to do that. But you can go from the aldehyde to the alcohol using NaBH4, okay? And also, you have not learned, but there is a way to go from an acid all the way down to an alcohol. That'll be one of the many reactions you learn in this course. You should just say, oh, LiAlH4 is a super, super duper reducing agent. It's a very strong reducing agent, stronger than NaBH4. Okay. Secondary alcohols are a little easier. It's just like you can oxidize or you can reduce, right? You can go up one state, you can go down one state. The oxidation reagent is PCC, the reducing agent's NaBH4. You can reduce an alkene, which basically means adding H2. Initially there's two CHs, now there's two CH2s. H2 palladium on carbon is the way you can do that. Interestingly, if you have an alkane and an alkene, you can kind of go back and forth. We call that redox cycling because we're oxidizing and reducing, right? We can go from the alkene back down to the alkane with H2 palladium. But what if we want to go the other direction? You can actually brominate. Remember that? Or brominate, Br2 adds a bromine to an alkane. And then you can reduce or eliminate with a strong base. And that can actually make the alkene. Okay, cool. So that's one thing. This is really important. This is all chapter 8 stuff. CC bond forming reactions. So organometallic reagents, remember that? That means carbon bound to metal. So here's an example. Ethyl bromide, you can add magnesium and it makes ethyl magnesium bromide. And then that is essentially equivalent to ethyl, 2 carbons, ... And that is a super reactive, like nucleophile. It can go attack stuff and ketones and aldehydes and things like that. Or you can do it with lithium. So a bromide reacts with lithium and makes organolithium, and then that thing is essentially carbon with the ... also. So there's super strong nucleophiles and also strong bases. So usually we use them as nucleophiles, so we go attack functional groups, okay? Here's an example. This is benzene CH2 MgBr, and this is kind of showing the mechanism of how it attacks acetone. It attacks acetone, a ketone. So the electrons of the bond, or you could just say, CH2 ... attacks the ketone. Electrons go up onto the oxygen. Then you have this intermediate, and then we grab a proton, usually as a second step, H3O+, and that makes an alcohol. So this is a wonderful way to make alcohols and make CC bonds. Okay. All right. That's one example. So I could either draw this thing this way, or I could draw like benzene CH2 ... There's another. So that's the alternate way I can draw this. Okay. Here's another example. Here's like a 3-carbon it's called organomagnesium, right? Organomagnesium. We also call it Grignard. So it's French, Grignard. And so this can attack the aldehyde, and then now you can see, oh yeah, we've attached it there. So the 3-carbon piece. And I put the little blue squiggly in there. That's a very useful thing to see like where the bond was attached, right? Alkoxide. What does alkoxide mean? The alkoxide is that kind of intermediate where, you know, it attacks, you get the O minus, the O minus thing. So you should be able to draw the alkoxide, and that would just look like this, but like O minus or O MGBR, right? Another thing to note, notice how when this attacked this aldehyde, where's the squiggly line relative to the OH? It's right next to it, right? The squiggly line is right next to the OH. Because sometimes when you attack, it won't be directly next door. Like here. Anybody remember the name of this functional group? Well, this is an aldehyde, but what's this? Begins with E.
Epoxy?
Epoxide, yeah. Yeah, and so here it's like the squiggle, the bond is nucleophilic, attacks the epoxide from the least hindered side, and now, and of course you could draw that alkoxide. It's going to look like this. But where's the squiggly relative to the OH? Oh, it's next door now. See the relationship up here versus down here? So that's how you kind of know. Here we're attacking a C double bond O, right? Aldehyde. Here we're attacking epoxide, and that's why the OH is the next door carbon. Okay, cool. So that's a really important distinction. And if you draw the little squiggly line, you can kind of see that. Okay, here's these reactions are called homologation. This is where you're like adding 1 or 2 carbons. Here's just like same thing. It's a Grignard. We're adding, what's this 1-carbon aldehyde called? It's not. It's an aldehyde, but it's a special aldehyde. It's
Formaldehyde?
Or maldehyde, you got it. It's a 1-carbon aldehyde, yeah. And yeah, so, and of course, now this is, how many carbons are here? This is 7, right? 6 plus 1 is 7. So 7 plus 1 should be 8. Do we have 8? 6, 7, 8. Yeah, 8. So you can double check your math there. And also here it's a 2-carbon epoxide. It's the same kind of thing. It's a 2-carbon homologation where we're adding 2 carbons. 7 plus 2 should be 9. And let's double check. Well, 6, 7, 8, 9. Yeah, it makes sense. Okay, and also where's the squiggly relative to the OH? Oh yeah, it's in the next door carbon, like we expect. Okay, good. These are some of the chapter 12 reactions. This would be a good, useful review sheet to just draw the reagents. Now, this isn't a super critical thing for chem335, but when we learn about alkynes and alkenes are kind of similar. So reviewing the reagents to make these things might be, it would be a useful thing, right? You should have learned this at the end of Organic 1. Like this one, anybody know, it's the mercuration, oxymercuration. It's the mercury acetate. It's all chapter 12. This is the boron one. Oh yeah, what's the name of these kind of alcohols? This is the alcohols on the more substituted. It's called Markovnikov. This one's on the less substituted side, anti-Markovnikov, right? Of course, how do you go from alkene to alkane? H2 palladium, you just saw that. 2 oxygens, that's the osmium one, OSO4. It's one of the weird chapter 12 reactions. Here are 2 ways of adding HBr. HBr Markovnikov or HBr anti-Markovnikov. This is just normal HBr. It's a simple reaction. This is HBr and peroxides. It was one of the things you should have learned at the end of Organic 1. Alkene to epoxide. Anybody remember? Alkene to epoxide. 5-letter abbreviation.
MCPBA.
MCPBA, yeah. And then, of course, you can add nucleophiles to the least substituted side. Okay. How do you add Br2? Any guesses? Oh, you add Br2. Just add Br2 as the reagent, right? That's easy. This is Br2 water. And how do you cleave an alkene? Like snip it. Snip the alkene into 2 pieces. It was ozone, O3. Is it O3, ozone? Okay. All right, good. Okay, so this is a very useful practice problem. I'm not going to do it all, but like, you know, part of this you can do kind of algebraically, right? This is 5 carbons, right? 4, 4, 5. It's 5 carbons. 5 plus 1 is 6. So this is also just formaldehyde. So it just attaches to the 1 carbon. It makes a new alcohol, right? This is attacking a secondary aldehyde to make a secondary alcohol. 5 plus 4 should be 9. So double check that it's 9. Is essentially this thing attaches there and makes the alcohol. Makes an epoxide. We attack the epoxide and it adds 2 carbons. Here we attack a ketone and it makes a new alcohol. So that carbon attacks that carbon, makes a new alcohol. Here it attacks the epoxide from the left side. Here it attacks the epoxide from the left side also. The D2O is just kind of a silly thing, just pointing out that this is super basic, and as a base, it takes the deuterium, which is just a heavy isotope of hydrogen. Okay, so being able to do the Grignard, like the attacks of these, it would be really useful. It will really help you for organic too. Good practice problems. I will have the key up probably within a week or so for this. All right. This is all on the website too. This thing is on the website. Here it's like you kind of do algebra again. 3 plus x is 4. 3 plus x is 4. X equals 1. Oh, maybe it's formaldehyde, right? Formaldehyde. Here it's like 2 plus x. 2 plus x is 1, 2, 3, 4, 5. 2 plus x is 5, so this has to be x equals 3. And if you look at where the OH is, it has to be a ketone, like a 3-carbon ketone. Here's a couple more problems you can try also. This is the same problem as that alkene one we just saw, but here I give you the reagents, and now you just fill in the products. See if you can do that. If you can do these problems, you're onto a well start for organic too, because we're going to build on this stuff, right? Here's the reagents, and this is very similar to that other sheet we just saw. It's just now you have to just draw the products in. Okay, we're done with the review, I think. Yeah, okay, let's get into the fun stuff. Our first organic 2 stuff. Somebody said, do I have an answer key for that? I do. I want to let you guys struggle a little bit, but if you really want the answer key before I post it, you can just email me. The best is to give it one try yourself. Okay. All right. So we're out of organic 1. Now we're going to organic 2. Somebody put their hand up.
Hi, Professor. I'm so sorry.
Okay.
In the middle of the review, I lost internet connection and I had to use my hotspot.
Yeah.
When will you upload this recorded video?
Oh, probably tomorrow. It's probably tomorrow. Yeah, it'll be. Yeah, usually it takes a while to process, and I usually leave work afterwards. But yeah, it's usually gonna be the day after the lecture, morning-ish. Right? Any other questions about that? All right. So we're into NMR, which is our first new organic 2 stuff. This is chapter 10, right? I kind of adapted / stole this lecture series from Donald Pavia. He wrote a good textbook, but I asked him for permission, so he allowed me to use these. And I've modified these lecture notes a little bit. They don't totally follow the Volhart and Shore book, but it's okay. It works, and the logic of this presentation will, I think, just make it'll be pretty easy to follow. But if you're reading along in the book, and we may deviate a little bit, in the end, after all these 7 little mini lectures, you will know this, all the key stuff you need to know about NMR. Okay, so what is NMR? We'll start with a theory. It's a nuclei, and that could be like a hydrogen atom, a carbon atom. They have this property called a spin. And it's kind of like the atom is spinning, right? Makes sense, right? But we don't know if they actually spin. It's kind of like they certainly behave like they're spinning, but it's hard to study atoms on the atomic level precisely. Now, the thing about spin is there's going to be a positive state and a negative state. So we call them, for a lot of atoms, it's going to be plus 1/2 and minus 1/2. It's kind of like it's spinning one direction or it's spinning the other direction. It's the easiest way to think about it. Each spin-active nucleus has a number of spins defined by its spin quantum number. You don't have to memorize any of these constants. Spin active means at least 2 spin states, because some atoms don't have any spin states. They don't have this property. Okay, so this shows a couple of nuclei. So proton 1H is this isotope of hydrogen. The spin quantum number is 1/2, and there's 2 spin states, so plus 1/2 minus 1/2. Deuterium actually has a different quantum number, and it has 3 spin states, so there's almost like 3 states of spinning. C12, this is an interesting one, because most of our carbon in our world is C12, right? Its spin quantum number is 0, and there's only 1 spin state. NMR doesn't work on carbon 12, so but fortunately, because NMR is so useful, there's also carbon 13, and we have lots of carbon 13. Well, there's less C13 in our world, but there's enough of it that we can actually do NMR analysis, and it has 2 spin states also. So the N14, it's nitrogen. There's like nitrogen NMR. It has 3 spin states. The 2 kinds of NMR we're going to talk about are proton NMR, which is the 1H, and the C13 NMR. Okay. All right. So number of spin states is 2I plus 1. Don't have to memorize that. I is the spin quantum number, and the most abundant isotope of carbon does not have spin. Okay, but we can do something called C13 NMR, which that'll be a little later in the course also. All right, good. The proton. We start with the proton. Okay, so these are the 2 spin states, plus 1/2, minus 1/2. And so the atom is kind of spinning one direction or sort of spinning another direction. That's the way to think about it. And the states are equivalent in energy. So it's like, you have a mixture, 50-50 mixture of the 2 spin states, right? These are equal in energy in the absence of a magnetic field. But when you apply a magnetic field, like a magnet or a big magnet, they actually have different energy levels, and we can actually distinguish the 2 spin states with a magnet. So now let's talk about this concept called resonance. So we can absorb energy into these spinning nuclei, and that can actually change the spin states. All right. So this shows a B0 implies a strong magnetic field. Here we have the 2 spin states now are different energy. So we have the aligned spin state and the disaligned or unaligned spin state. Okay, so when you have 2 different spin states like this, we can actually start studying this phenomenon. It's going to tell us, it's going to be useful to tell us basically the chemical structure of an organic molecule. We'll get there in a bit. Okay, so the big things we need though are a spin-active nucleus, like proton, a strong magnetic field, and then we're going to have to be able to detect this. So there's going to be a detection process. All right. Okay, so the other interesting thing, in addition to the 2 spin states, is that if we apply radio frequency, basically like the frequency of radio, like listening to the radio in the morning, essentially, it'll actually go from the low energy, it'll absorb the energy and go from the low energy to the high energy, and that can be detected, and that's essentially the basis of NMR. We'll see how it's useful in a second. It really does give you hints on the chemical structure, which is really cool. Okay. And the other thing is that this all depends, this energy separation. So we have a low state and a high state. It all depends on the magnetic field strength. So if you have no magnet, it's called degenerate. Degenerate means same energy, right? You start applying more and more magnet, you have a big difference, right? What if you want this to be even a larger difference? You just use a larger magnet, right? And that's going to, again, that'll all be related to the chemical structure here in a second. but the big, yeah, okay, we'll just keep going with that. Oh yeah, and the difference in energy levels is equal to Planck's constant times the frequency of light, of radio frequency light, which is also related to another constant times the magnetic field strength. So the big thing is, as you get more magnet, which is also increasing B0, right? That's the magnetic field strength. We have a higher frequency, right? More magnet, more frequency. Okay. Okay, so this is a scary looking equation, but it's really not a big deal. You don't have to memorize it. This is just showing what I just said. The energy difference is related to a constant times the magnetic field strength, which is also related to basically the frequency. And if we play around with this equation, we basically can see that the frequency of the light, the RF light, is related to a constant called the gyromagnetic ratio, which is just a constant that different nuclei have. So hydrogen has one, C12 or C13 has one. 2 pi is a constant. So this is all a constant. The basic idea is the frequency is related to the magnetic field strength, which I've said a few times now already. Okay, so this gamma constant, it just is related to the different types of nuclei. Okay, proton or C13, etc. Okay, another effect of a strong magnetic field. When a spin-active hydrogen atom is placed in a magnetic field, it precesses. And that basically means it spins around the axis. It spins around in a frequency. It's like spinning, 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 right? That's what we mean by precess. So a nuclei will kind of spin around the axis. So it's precessing, spinning around at frequency omega, is spinning around, right? And another interesting thing is that if we zap the nuclei with light, which of a specific frequency, when light equals that frequency, the energy will be absorbed. So the nuclei actually absorbs the energy, and its spin will invert. So it flips. It flips to its other spin state. Okay. All right. And again, this is all related to the chemical structure. That's why we care about it. The basic theory is not that important, though. So if the theory is a little confusing, it's not a big deal. We'll see how it's related to the structure, organic structure, in a bit. Okay, there's a little bit more. This just shows, okay, first of all, that we have a couple nuclei, proton, deuterium, and C13. All of these are spin active. And they all have a gyromagnetic constant, which is this gamma number. They all have a different number. The main thing that this is showing you is that, again, just like I said before, is that the frequency and the magnetic field strength are related. Okay. Interestingly, one thing that you'll see if you do real NMR, like in your research or something, is that the frequency of like carbon, for example, is always 1/4 the frequency of proton. So if your NMR is like, we'll say 400 megahertz for proton, your NMR will be 100 megahertz for carbon. So there's a 1/4 relationship, and that's what it's showing here. The carbon's always at a 1/4 of a frequency of proton. Okay. Okay. Okay, so now we'll actually show kind of what this looks like, and we'll talk about how it relates to structure in a bit. This is the old school, 1960s. Okay, so the basic idea is you got a magnet. You got a magnet. Somebody said, so any abundance greater than 0% means structure is spin active. The big thing, well, the requirement is you need a spin active nucleus. So for us right now, it's proton, 1H, or C13. Those are the main ones I'd consider. Spin active means at least 2 spin states. Okay. Okay. So here we go. Here's a big magnet. You got a big magnet. You have a sample. That's your chemical sample. And you have a RF oscillator, which is basically just generating RF, radio frequency. And then you have an RF detector. So you're generating RF frequency and you're detecting it. And then you have a recorder. That's essentially what an NMR machine is, all right? And if you do that, let's just imagine this molecule. This is, what functional group is this? It's a, what is that? It's a ketone, right? Ketone functional group. If you do this for this molecule, look at that, the frequency that we have three different types of protons, right? We have the benzene, we have a CH2, and you have a CH3. They all kind of absorb different frequencies of light. That is cool, right? Because then if we have this, we'll take this many steps further, but basically different types of protons process at different rates in the same magnetic field. So we can basically distinguish the different parts of a molecule. That's essentially what NMR allows, okay? So we have this big magnet and we do this experiment, and then you can see there's detection at different frequencies. Okay, and then what they do in these classic million-year-old instruments is they basically scan the magnetic field. So they can change the magnetic field strength, and they go from kind of like, we'll say, the low field to the high field. And then all you do is just change the magnetic field, and then you look for detection at different, the frequency will change as the magnetic field strength changes, and you're basically just detecting absorbance throughout this series. And so you basically get a spectrum of like the different absorbances. And this is what it looks like. So this is this phenylacetone molecule. And you can basically see, this is your first NMR for the course. You basically see this big peak right here. That's 5 protons. Why do we have 5 protons there? Well, how many protons are on the benzene? 1, 2, 3, 4, 5. Oh, good. Okay, there's 5 protons. We also have a CH2 group. Oh, 2 protons. Okay, good. We have a CH3. Oh, 3 protons. All right. So a lot of what we're going to do is be able to interpret this kind of spectrum. And eventually, we're far away from it. I'm going to be able to give you a spectrum, and you can figure out the structure. So somebody said, is this similar to IR spectra? The answer is absolutely not. It's a good question, though. It's a great question. Is this like IR spectra? No, not at all. IR is different frequencies and a different phenomenon. IR is really functional groups. Like IR will show, there's a stretching frequency for a ketone, and you can kind of say, oh, I have a ketone because I have an IR stretch. This is really about the structure of the molecule, all the protons. Totally apples and oranges from IR. Okay, so every different type of proton comes at a different place. It allows you to see how the many types of hydrogens there are, right? And you can from just looking at this, you can say, well, we have 3 kinds of hydrogens, right? We got the benzene, we got the CH2, we have the CH3. That's cool. And we're going to take this a million steps further. Okay. Okay, so now let's talk about the newer modern instrumentation after the 1960s. This is called pulsed Fourier Transform technology. This is the modern type of NMR. We have 2 of these fancy NMRs in our first floor of Thornton. They're about $500,000 each. Very expensive toys. Okay, we all get to use them. The people that do research, or you get to play with $500,000 instruments. Okay, so here are the ideas that are a little different. Okay, we have the magnet. Now what we do is we blast RF of it's called broadband pulse. So it's a pulse of all the frequencies of RF, all simultaneously. And what that does is it causes all of the protons in the molecule to get excited, right? They get excited because they get blasted with RF, and they all jump up to the high excited state. And and essentially, once they do that, then they start decaying. They get excited, and then they decay. And that's this. You can see what that looks like. This is the decay. It's like, oh, it's like we got excited, decay, 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 excited, decay, 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 excited, decay, decay, decay. And all of these, all of the different protons, all have different half-lives and kind of like a different decay rate. you add them all up and it looks like a mess. Is that useful? I don't know. It looks like a totally unuseful thing, right? This is called a time domain spectrum, okay? This is a time domain spectrum because the time is the x-axis, right? And we see this decaying over time. It's all the frequencies all added up, and it's called time domain, all right? And then what's cool though is you can do this trick called Fourier Transform. This is a mathematical trick that you might learn about this in an engineering course. But it's essentially a very difficult mathematical process that computers do very easily. It basically turns a time domain spectrum into a frequency domain spectrum. And the frequency domain is the one we like. It's sort of like, oh, we see the different frequencies, right? So essentially you take your mixture of frequencies, you do the Fourier transform, and now we got our beautiful little spectrum, which shows the 3 different types of protons. All right. So on how, this is insanely complicated thing is really a button on the computer. You're like, all right, boink, and then it does it for you. And it's a very complicated mathematical thing, but that's what Fourier transform does. It converts time domain into frequency domain. Okay. Okay, so let's talk about the 2 types of NMR. We have continuous wave and Fourier transform. Okay, so continuous wave is the old one. Nobody does that anymore. You may have done this if you took community college somewhere. Sometimes they have old NMRs just at community colleges, and the nice thing is you can just do it. You can do it on the old continuous wave NMR machine. Continuous wave is the old method. The magnetic field is scanned from low field to high field, while we just have a constant beam of radio frequency, right? It requires several minutes to plot NMR. It's very slow, it's not very useful, but it's what we had in the 60s. Then we have pulsed Fourier transform NMR, very fast, it's very low noise, it's very low noise. It's pulsed, data collection, and the computer does everything. The computers are amazing now and makes this all very simple. The pulse data can be repeated many times, and if you do it multiple times, you can average the data and you get an improved signal. So, like, imagine I do a pulse and I get a very poor signal, very poor signal. Then I do it again. Oh no, poor signal. What if I do this 20,000 times? Oh, you just do it 20,000 times. Beautiful. Now I have a beautiful spectrum. So that it's nice that I can repeat this 20,000 times and then convert a really garbagey looking spectrum into a very beautiful spectrum, right? That's why we use Fourier transform NMR, because we can do multiple acquisitions, average them out, and you get a beautiful baseline spectrum. Okay, so what are the instruments at SF State? We have, well, this is old, is gone. But these are all Fourier transform. We probably had a continuous wave a million years ago here before I was born. This is a 300 megahertz, kind of old one. This is a newer 500 megahertz. This one we got a few years ago. This is super duper cool. It's got a robotic auto sampler, so you can I can put like 20 samples in. Here's 20 NMR samples. Press go on the computer, and it'll do 20 acquisitions all automatically. It's got a little robotic booster, so it'll boost the sample up the little thing and inserts it in the machine. Everything's automated. It's super cool. Many people have many companies, most companies have these kind of fancy ones nowadays. The provided slides don't have the last picture. Okay, email me and I will update it. I'm sorry. Maybe this isn't on the website, but thanks for noticing that. This is the last slide though. Yeah, it might be on style 2. Yeah, good. Okay, good. All right, let's keep going. All right, so we're into number 2, and remember these aren't, I would say 7, some of these are like 3 or 4 slides long, but there's a couple things we got to talk about. One of them is called integration. One of them is going to be called chemical shift, which is kind of like the position on the axis, the X and Y axis. There's a couple other little things, but integration is the first thing. Okay, back to our spectrum. Phenylacetone. How many types of protons? 3. Aromatic, CH2, CH3. each different type of proton comes at a different place. It tells us how many types of hydrogens are in the molecule, right? These 3 peaks mean 3 types of molecule, 3 types of atoms, right? That's kind of cool. Integration, you've probably heard the word integration, maybe from calculus or something. It's the area, right? Area under the curve. That's what integration means. So it's the relative number of each type of hydrogen, and the property is called integration. So integration is the determination of area under the peak. That's all it means. Integration is the area under the peak. Integration is proportional to the number of hydrogens, right? We just saw that, actually. Let's go back. The area under the curve is essentially 5 to 2 to 3. So if you calculate the area under the curve, it would be 5 to 2 to 3. Okay. That's what I say. It's proportional to the number of hydrogens composing a peak. And so there's kind of 2 ways that integration are done. This is kind of the old way, maybe continuous wave style. Like you're given a little graph paper printout, and you're like, you can kind of calculate like the number of boxes, and you're like, oh, well, that's about 15 and a half. That's about like 22 div basically means 2.2 boxes. 55 kind of means like 5.5 boxes. This is like roughly 3.2 boxes. So you can kind of do this, with graph paper. This is old. Nobody does this anymore. But that you can see that it correlates, right? 5 to 2 to 3. 5 to 2 to 3. Okay, so it's roughly 5 to 2 to 3 is, and that correlates to the number of protons in the molecule. Now that we have modern computers can do area under the curve super easily, and so this is like a modern NMR of the same molecule, not a different molecule, but it's also 5 to 2 to 3, so the way this works, and you're going to see, we're going to study, integration a little bit, and also like you're going to learn that like a CH3 group. This is a CH3, right? CH3s usually come around the 1 to 2 region of the spectrum, and so kind of figuring out like which of these is the CH3, which peak is a CH3. We were like, well, it's probably the thing around 1 or 2, and that's how we know that this is the CH3. But look at the relative area. This looks kind of big. This looks kind of small. This looks like a little bit larger. Given that we know that this is probably a CH3 because it's around 1 to 2, we can calculate from the area that number. Take that number and divide it by 3, and it's roughly 11.3. And that is essentially the amount of integration for a single proton, right? We have a CH3, it's a single proton there is about 11.3. And if we have that number, then we can do that, divide these numbers, which are the areas, by 11.3, and we're like, okay, well, this 21 divided by 11.3 is 1.9. About 2, right? 58 divided by 11.3 is about 5.14. Now you can also see 5 to 2 to 3, 5 to 2 to 3. So it's the integration is the relative, it's proportional to the relative number of protons in the molecule. Okay. So in reality, it's 5 to 2 to 3. Another thing, well, actually, let's keep on. We'll show an example now. Accounting for the hydrogen atoms in a molecule. Let's think about an example here. So this molecule, how many types of protons are there? So you can say it in chat. It looks like we have a chlorine, how many types of protons? Yeah, somebody says 3. You're right. It's 3, right? You have a CH2, you have a CH2, and you have a CH3, right? That makes sense. So how many NMR signals are you going to see? Probably 3, right? Yeah, you're expecting 3 protons. And what's the proportion going to be? Well, there's 2 to 2 to 3. Maybe it's going to be 2 to 2 to 3, right? The integration is predicted to be 2 to 2 to 3, right? And that's exactly what you expect for integration. So when you see this red line here, the red line, that is a indication of the integration, okay? So can you see how it looks like maybe if that's like the one distance, well, this looks like the same distance, right? These look about the same distance, right? Is this the same distance or larger? Like this versus this. That peak at 1 is probably a little bit larger, right? So now you can kind of see, oh, it's 2 to 2 to 3, right? It's 2 to 2 to 3. So that's an example of like, the red line is the integration. It's just the area under the curve, right? We can see 2 to 2 to 3. There we go. And looking at the size of the red line, you know, this is this area versus this, which is the area of the middle peak versus this. You can see 2 to 2 to 3. Okay. Ignore the multiple pattern. What's the multiple pattern? That's like, see how this is, it's called a triplet. It's like there's 3 peaks here. This is going to be called like a pentet or a hextet. It's the number of peaks inside, and this is also called a triplet. That's something later in the core or later in the chapter. So let's ignore that for now. And also, the assignment of the peaks will be much easier in a few minutes. Like you'll learn very quickly that this one is going to be the one next to the chlorine. This one is going to be the one in the middle, and this one's going to be the one on the right. But you're going to learn why in a second. Somebody said, is the reason the CH2 on the left is farther away because of the chlorine? That is true, but we'll explain it. You'll understand why in a second. Okay. Okay, here, how about this one? Molecular formula, C5H11Br. How many protons are here? 11, right? So when we figure out, we were going to count for the hydrogen atoms when the structure is not provided, we can use the molecular formula, meaning I'm going to have to look at the integrations and have it add up to 11. Okay, so we'll see it. We'll show the spectrum now, and let's see if we can figure out 11. Okay. Okay, so here it is. So if you look at the red line, this is a number of protons. This little guy is a number of protons. This little guy is a little number of protons, and this little guy's, this larger guy is a number of protons. What did we say comes around 1-ish? Maybe up to 2, but definitely at 1. There's only one thing that comes at 1. CH what's? CH3. Somebody said CH3, right? Okay, so it could be 1 CH3, but maybe it could be 2 CH3s. Because if it's 2 CH3s, what's 2 CH3s is it's 6, right? If this is 6, what's 11 minus 6? 11 minus 6 is 5, right? If this is 6, then what do you think the left peak and this little guy and this one are? Maybe it's, you have 5 more to account for. Maybe it's 2 to 1 to 2. That's 5, right? 2 to 1 to 2 is 5, plus 6 is 11. That's exactly it. So if I'm given a molecular formula like 11, and we know only one thing comes around 1, definitely one thing comes around 1, it's CH3s, right? This can't be 1 CH3, because if this was 1 CH3, how could you account for 11 protons with the remaining integration? Can't work, right? It's either going to be 2 CH3s or maybe 3 CH3s. What is 3 CH3s? There'd be 9. But if this is 9, what's 11 minus 9? Is 2. This can't be 2 protons, right? The only logical thing is 6 protons here. 2 CH3s, 2 CH3s is 6, and we have 5, and then it's going to be 2 to 1 to 2 to 6, which is 11, right? That's going to be a skill you develop. So this is just a first example of this. We're not going to even show the structure of this, I don't think. I just want to practice this technique of figuring out 2 to 1 to 2 to 6, okay? All right. Useful hint, signals that come around 1 to 2 are usually going to be around 3. Now these are not CH3s. Obviously, they can't be, right? Because the integration is very small. But certainly something that's at 1 is almost always going to be that's 1 or 2 CH3s. Okay. So that one would be methyl. Yeah, this is actually 2 methyls, 2 identical methyls. 2, yeah. But again, we're not going to show the structure here because that's beyond our level skills yet. Very soon, probably by next lecture, you're going to be able to figure out the chemical structure of this. Sounds scary, right? We're going to interpret each of these different things and be like, okay, yeah, but and basically put together a chemical structure. Okay. Okay, diamagnetic anisotropy. This sounds like a scary, scary set of syllables. Why protons absorb at different frequencies. So this is kind of like why we get things like a chlorine might be a little bit to the left, for example. It's going to be a concept called shielding by valence electrons. Okay, so first thing, here's the magnetic field, yeah? And then you have electrons around a nuclei, like a proton, right? Pretend there's a proton, it's got some electrons. When the magnetic field is applied, the electrons kind of swirl around, and they actually create an opposing magnetic field, okay? You have an applied field, you have an opposing field. And the valence electrons that oppose the magnetic field, they shield the nucleus from the full effect of the applied field, okay? So we might call this a shielding effect. So electrons around a nucleus, like an I-hydrogen, they actually will shield the nucleus from the effect of the magnetic field, okay? All right, we'll see why, we'll take this a step further in a second. But there's a shielding, an inherent shielding effect. What if these electrons get sucked away? Like, say I have a chlorine. I have a chlorine over here, electronegative chlorine atom, right? What happens to the electrons? Oh, they get sucked away. They get sucked away, right? The chlorine's over here, pretend. Oh, the electrons get sucked away. No more electrons. Do you have any more shielding? No, you don't. It's called deshielding, right? And that's why, as we just saw, like a chlorine will suck a signal kind of to the left of an NMR. We'll see that example again in a second. Okay, so all types of protons have different amounts of shielding, right? The left side are called less shielded, or you can say deshielded. The right side are highly shielded. So the right side protons are highly shielded because there's a lot of electrons around. Things that are on the left are highly deshielded, okay? They all respond differently and appear at different places. That's why NMR is so cool, is because the different types of protons come at different places. That's why NMR contains useful information. Different types of protons appear in predictable places. Not only different places, but predictable. Like we can make little charts. Chemical shift. Okay, so chemical shift just means the position on the x-axis, all right? So first of all, the 0 point is called, well, we reference based on a molecule called tetramethylsilane, TMS. So every 0 point's always the same molecule, TMS, all right? Now, and then you could assume the signals to the left would be in an amount of hertz, right? The problem with that is, remember when we have different magnets, what happened to the amount of hertz? Like a big magnet, small magnet. The amount of hertz depends on the size of the magnet. So this is actually kind of annoying, because then it would mean that a different magnet would give you a different NMR spectrum, right? So what modern NMR does is we kind of change this to make it independent of the magnet, okay? Because recall from earlier, stronger magnetic field causes the instrument to operate at a higher frequency, right? We said that? The frequency is kind of correlated to the magnetic field strength, right? So if you have different frequencies, well then your NMR axis is totally different. This would be really annoying, right? So the shift observed is in hertz, is kind of dependent on the spectrometer frequency, right? Well, we basically probably figured out in the 60s or something, is that we can kind of normalize the x-axis to be independent of the magnetic field strength. Okay, so there's this formula, chemical shift, that's basically the x-axis, is called delta. It's the shift in hertz divided by the spectrometer frequency. And that gives us a universal x-axis called ppm. So everybody on this planet that does NMR, we use this. And it's great because every NMR on this planet has this consistent x-axis. Okay, so we normalize the chemical shift to be independent of the spectrometer frequency. Now this is all done by the computer. It's not like we have to do this or you have to calculate this. This is all done automatically. Okay, so now we have a universal shift in ppm. And as you go left, it's called downfield. And is left de-shielded or more shielded? We said left is de-shielded. Okay, so that'll be, we get into that next time, but let's just finish one more slide. The ppm is universal in modern NMRs since the 70s probably. Okay, and let me see. I just want to I'll stop on this. Okay, so this is going to be where we're going to go next. You can see that different types of molecule or different types of atoms on your molecule always come at the same place on the ppm scale, which is super cool. That's going to make this so useful. Like a benzene always comes around 6 to 9. Aldehyde always comes 9 to 10. Carboxylic acid always comes to 10 to 12. Alkenes come with their 6 to 4. And if you have an electronegative atom, like a chlorine, right? A chlorine or something, if it's a CH where it's next to an electronegative atom, it comes between 3 and 4. Okay? So we're going to see tons of examples, and you're going to kind of ingrain this into your head. This will also be given to you on the exams and stuff too. So you don't have to memorize this. If you can kind of memorize it, it'll help you. And lastly, oh yeah, next to a pi bond, so like next to an alkene or next to a benzene is 2 to 3. Aliphatic is just like a boring CH3 next to nothing. I think we're done. I think, and also I'm gonna, I'll probably hang out a bit. So if you have any questions, I can talk. It's like a mini office hours. You're always welcome to kind of talk to me afterwards. But I think for today we got a little bit of NMR, and we have a lot more fun NMR to talk about. All right. So I have a question.
Sorry, what do the numbers represent again?
This is that ppm scale.
Yeah.
We also call it chemical shift. Yeah, chemical shift. So if I say, oh, a signal comes at 3.5 ppm, you know, that would be, oh, it's maybe next to a chlorine or something like that, right? Yeah. So it's just it's the x-axis on an NMR spectrum.
Okay, thank you.
Now, what is the integration? Integration is not. This is not integration, right? Integration was the area under the curve, which is just proportional to the number of signals. So it's kind of like we have two pieces of information. We have integration, right? We have chemical shift. The third one is going to be splitting. That's the funny thing we saw earlier with like the little triplets and quartets and doublets, and that'll be another very important piece of information. We're just not there yet. Any other questions? Something we'll have to memorize. Somebody said, like, is this something you have to memorize? No, but you will. It'll be helpful, and you might print this out for your notes just to study. It's also on the syllabus, so you should print out the syllabus anyway. As you start doing NMR problems, if you have no idea where any of these come at all, it's just gonna be a little more difficult. But I will always provide this on the exam. So this is a very useful reference material. Every exam will have this on it. Any other questions? Are you guys psyched, or is this kind of scary?
Scary.
It's a little scary.
Yeah,
but you barely even learned it, you know. We just started, and you'll love this. Usually, once we get a little further, people are going to say NMR is the coolest thing you've ever learned before. I don't know. I as a research chemist, you know, I do NMR multiple times a day. I just run down to the first floor and I do this, and I can figure out a chemical structure, right? Like very quickly. It's very complicated chemical structures, not these simple ones. I can do crazy molecule with 20 different types of protons and use this to figure out the chemical structure. It's really cool. How much memorization compared to organic 1? Somebody said. Well, that's a hard question. I mean, yeah, similar. I mean, you can have a lot of new reactions. We're not even in the reactions yet. But the biggest recommendation is when we get to the reaction part, have a method to absorb them, and index cards is a way to do that. If you didn't do index cards in Organic 1, maybe when we get into the alkyne chapter, which is a lot of reactions, maybe that's a good time to start. You know, reaction on the front, mechanism on the back, and when you do those exams, it's really helpful. I've got to work on the machine a little inductory Toga's lab. Sweet. Yeah. I mean, yeah, we have students in this class that have gotten to do NMR in research, which is super cool. Also, if you're in Organic 2 lab, you're going to be kind of, well, you're not going to personally do the NMRs just because there's too many students. But usually what we do in the Organic 2 lab is your first experiments to make aspirin, right? And so you synthesize aspirin. And how do you determine you made aspirin? You take an NMR of it and you see, oh, I see all the different parts of aspirin. Okay, there's a CH3 group, there's a 4, aromatic CHs. So every experiment in Organic 2 lab, we will give you NMR. Often what we do for Organic 2 lab is everybody puts their sample in a vial, and then we mix up the vial and we go take one NMR, and then you get the class sample. So you get to see, oh, that's the class sample of NMR, super cool. And you get to interpret it. You get to interpret the NMR. Like we give you the NMR and you have to figure out, okay, this is the CH3 group. That's the orthos CH on the aromatic ring, etc. And that thing I mentioned, NMR-DB, which on syllabus or on the website, that is a cool utility that lets you draw a chemical structure and predict an NMR. It is called a simulator. So you'll use that in your Organic 2 lab also. It reminds of quantitative analysis. I don't think this is like the quantitative analysis because it's more qualitative. but qualitative, but very definitive, right? NMR is definitive. But it's not that quantitative, right? It's not like you're analyzing the amount of copper iodide or something, or like it's a different kind of analysis. But I love it because it directly correlates to the chemical structure. I mean, you can imagine any, if you want to have fun, pick a molecule that Tylenol or Taxol, strychnine, and Google NMR, strychnine NMR. Try that, strychnine NMR. You'll get to see what the NMR spectrum of it. Strychnine is an insanely complicated molecule, insanely complicated, like 20 chiral centers, and it's got a very interpretable NMR. Or aspirin NMR. You can do that. All these things you can do now. You can't totally interpret it, but you get a little further. You can do that. So. Are we going through reactions as fast as chapter 9, 11, and 12 in this class? It is spread out. I mean, we just reviewed 8, 9, and 12 in like 5 minutes. Where obviously chapter 13 you don't know. You don't know anything about alkynes. So we'll go through it fast, but at a rate that you can pick it up. And you can always rewatch the old videos or the new videos. But yeah, we're going to go kind of at the rate of like organic, how we did it in Organic 1. Any other questions? All right. And big thing though is, remember exam 1 will be chapters 9, 10, and 13, and just stay on top of it. Don't get behind. All right. This might be a useful thing to mention. There's a lot of people still here. The exam type problems for NMR will be exclusively here's an NMR and here you figure out the structure. That's far away. Right, we got a lot of fundamentals to do first before we're there. So the annoying thing is we're going to do a lot of fundamentals, and then almost like the last thing we get to in chapter 10 will be how to actually figure out a chemical structure. So if you're wondering like what am I going to have to learn and know, you know all this stuff, but the exam problems are going to be we call it structure elucidation. We're just not there yet. But try the homework and try to read a little bit ahead, and then you'll do great. All right.
Sorry, what were the chapters on again that exam 1 will be on?
Exam 1 will be chapter 10 and chapter 13.
Okay, thank you.
And if you're a real crazy go-getter, all of the videos are already recorded from a year ago. You could watch them over the weekend and be an expert for the exam 1 if you're crazy. And if you want to watch ahead a little bit of the NMR stuff, like what we're going to do next time, it's all on the website. It's the beauty of YouTube, and that is actually one. As of a year or two ago, my students didn't have that option, but now we have it all pre-recorded, so it helps you. All right. Cool. Well, have a wonderful night. Hope your other classes are cool also-ish, or I don't know. I think this is going to be your funnest class, I think.
One quick question.
Yeah.
So like if one were to like go back and like rewatch this lecture, like what would you put what in your mind do you want us to like pull from what you just covered, like most importantly, I guess?
We're still in the really fundamental stuff. Basic idea of integration, basic idea of a chemical shift. I think the theory, and all that gyromagnetic ratio and the all that stuff, that's not that important, really. I don't want to leave you hanging and not present it at all, but I'm not going to test you on the fundamental theory stuff. Just understand, oh yeah, you got 2 spin states and they flip. That's, but the exam is not going to be any of that stuff. The exam is really going to be a application, like using it to solve structures. And the other thing is you're going to have an NMR problem on every one of the exams, all the way to the end. Exam 1, Exam 2, Exam 3, Exam 4, and Exam 5 will all have NMR problems. So if you got to become a really good expert, and then you're going to get 10 points, 15 points on every one of those exams, and it's really going to help you. Some people will like miss a NMR lecture, and then they're going to be toast on all those exams. You're going to lose a lot of points because they all have NMR questions. So NMR is very cumulative in this course, right? So get a really good NMR. I think next lecture will be very critical because we have a lot of cool stuff to talk about. And but if you want to watch ahead, it's all last year too. Get better, learn it any way you can, right?
Well, thank you so much.
All right. Cool. All right. See you guys.
Have a good night.